This is week 3, data processing, asymptotic equipartition property, lecture notes in information theory. I am Hikmet Kamberay, a professor at the International Balkan University. An outline of the presentation for today includes log sum inequality, data processing inequality, Fano's inequality, asymptotic equipartition property, and extra exercises. First, I'll talk about the log sum inequality. Consider the following non-negative numbers, A1, A2, and so on, AN, and B1, B2, and so on, BN. Then, sum of I from 1 to n, AI, log with base 2 of AI over BI, it is greater or equal to sum of I from 1 to n, AI, times log with base 2 of this ratio, sum of I from 1 to n, AI, over sum of I from 1 to n, BI. Equality holds if and only if AI over BI, it is a constant. First, we assume that AI and BI are greater than 0 for every I. Furthermore, the function f of t equal to t log with base 2 of t is a strictly convex function because the second derivative of f with respect to time t, it is equal to 1 over t log with base 2 of e, which is always greater than 0 for every t greater than 0. Using the Jensen's inequality, we get that the sum of I from 1 to n, sum alpha I, f of ti, it is greater or equal to f of sum of I from 1 to n, alpha I ti. For every alpha I between 0 and 1, including 0 and 1, and sum of I from 1 to n alpha I, it is equal to 1, which satisfies the condition of being a property mass function. Taking the following, alpha I as bi over sum of j from 1 to n bj, and ti equal to ai over bi, we can get that sum of I from 1 to n, bi over sum of j from 1 to n bj, log with base 2 of ai over bi, it is greater or equal to sum of I from 1 to n of this ratio, bi over sum of j from 1 to n bj, log with base 2 of sum of I from 1 to n of this ratio, ai over sum of j from 1 to n bj, which is what we wanted to prove. Now let's prove the second part of the theorem. Consider ai over bj as a constant, let's say c. Then log with base 2 of ai over bi, it is equal to the log with base 2 of c. Then sum of I from 1 to n ai, it is equal to c sum of all i's bi. Therefore, we can say and hence I from 1 to n ai log with base 2 of ai over bi, it is equal to the sum of I from 1 to n ai log with base 2 of c. Or we can further write and as a sum of I from 1 to n ai log with base 2 of this ratio, sum of I from 1 to n ai over sum of I from 1 to n bi, which is equal to sum of I from 1 to n ai log with base 2 of c. Thus, equality holds if and only if ai over bi, it is a constant, which is assumed at the start of this second part. As a remark, we use the following: 0 log with base 2 of 0 equal to 0, a log with base 2 of a over 0, it is infinite for every a which is greater than 0, and 0 log with base 2 of 0 over 0, it is equal to infinite. The second, we introduce the relative entropy inequality theorem for a discrete random variable x and two probability mass functions, let's say p of x and q of x. From the alphabet chi, we show that the relative entropy of p from q, it is non-negative. Note the equality here holds for p of x equal to q of x for every x from the alphabet chi. This is something that we showed also last week, but we are going to prove it in a different way. From the definition of the relative entropy, which we gave it also last week, The relative entropy, it is equal to the sum of all x's from chi p of x log with base 2 of this ratio p of x over q of x. Now, if we take AI equal to p of x and bi equal to q of x, for every x from the alphabet chi, we can write that d it is equal to sum of all x's from chi p of x log with base 2 of p of x over q of x. Now, using log of sum inequality, the theorem that we just showed, we can write that this is greater or equal to sum of all x's from chi p of x. All this one multiplies log with base 2 of this ratio, sum of all x's from chi p of x over sum of all x's from chi q of x. Now, this is equal to the first sum here, sum of all x's from chi p of x. It is equal to 1 because p of x, it is a property mass function and it satisfies the normalization condition. Similarly, also for sum of all x's from chi q of x, also it is equal to 1 because q of x, it is a property mass function. And then we arrive to this expression 1 times log with base 2 of 1 over 1, which is equal to 0 because log of with base 2 of 1, it is equal to 0. 1 times 0, it is equal to 0. Now, to prove the equality, take the p of x over q of x equal to some constant. In that case, this constant will be equal to 1. Then we'll have that the relative entropy, it is equal to the sum of all x's from chi, p of x, log with base 2 of c, which is a constant on that case. Now, log with base 2 of c as a constant, I can bring it outside the sum. Then I will be inside the sum with sum of all x's p of x, which is equal to 1 because p of x is a PMF. Then I have log with base 2 of c. For c equal to 1, then this becomes equal to 0, which indicates that relative entropy is equal to 0 if and only if p of x it is equal to q of x, or for every x from chi or c it is equal to 1, which is the same. Now we are going to show another theorem, which is convexity of relative entropy. So we have to show that the relative entropy is a convex for two given property mass function p of x and q of x discrete random variable drawn from the alphabet chi. That is, for any two pairs p1 q1 and p2 q2, we have this equation. D of lambda p1 plus 1 minus lambda p2 from lambda q1 plus 1 minus lambda q2. It is less equal to lambda relative entropy between p1 and q1 plus 1 minus lambda relative entropy between p2 and q2. And this is for every lambda on some interval 0 to 1. Now, to prove this theorem, we start with taking only one of the terms of the relative entropy on the left-hand side, and we use the log sum inequality, but in the inverse direction. So I'll have this one, lambda p1 plus 1 minus lambda p2 log with base 2 of this ratio, lambda p1 of x plus 1 minus lambda p2 of x over lambda q1 of x plus 1 minus lambda q2 of x. Now this is less equal to lambda p1 of x log with base 2 of lambda p1 of x over lambda q of x plus 1 minus lambda p2 of x log with base 2 of 1 minus lambda p2 of x over 1 minus lambda q2 of x. Now, if we sum over all x's from chi, we get the following. Sum of x's from chi of lambda p1 of x plus 1 minus lambda p2 of x log with base 2 of this ratio, lambda p1 of x plus 1 minus lambda p2 of x over lambda q1 of x plus 1 minus lambda q2 of x. Now, this is less equal to lambda sum of all x from chi p1 of x log with base 2 of lambda p1 of x over lambda q1 of x plus 1 minus lambda sum of all x's from chi p2 of x log with base 2 of 1 minus lambda p2 of x over 1 minus lambda q2 of x. Or we can write the first gives you the relative entropy of between these two property distribution, lambda p1 plus 1 minus lambda p2, and lambda q1 plus 1 minus lambda q2 less equal to, then the right-hand side gives us lambda times the relative entropy between P1 and Q1 plus 1 minus lambda relative entropy between P2 and Q2. And this is the proof of what I wanted. Now we are going to check the concavity of the entropy itself. Now let x be a discrete random variable with some property mass function P of x. We want to show that the entropy H of P is a concave function of the P. We showed on the last week, all right, week number 2, that the entropy can also be written in the following: H of P, it is equal to log with base 2, cardinality of the alphabet set chi minus the relative entropy P from the uniform property mass function U of x, which is 1 over cardinality of chi, all right? And chi itself, it is the cardinality of the alphabet chi, or the number of elements in the range of alphabet chi. Since log with base 2 of chi is a constant here, and moreover, the relative entropy is a convex function, then from the definition, minus a convex function gives a concave function, then this shows that H of P is a concave function. Now we are going to prove another theorem, which is concavity of the mutual information. Now let x and y be two discrete random variables with joint property mass function P of x and y, which can be written based on the property and statistics as P of x times conditional property P of y given x. We want to show that the mutual information I between x and y is a concave function of P of x for fixed conditional probability P of y given x, and the convex function of P of y given x for fixed P of x. Now, first we start with the expression of the mutual information. So the mutual information between x and y is equal to the difference between the entropy of y minus entropy of y given x. Or we can write it entropy of y minus, then I write the conditional entropy as sum of all x's from chi, P of x times the entropy of y given x equal to x. Now for fixed P of y given x, right, then the mutual information between x and y is a function of P of x and P of y, where P of y is a concave function of P of y because it is an entropy, and we showed this one on the previous theorem. Moreover, from property and statistics, we can write P of x, it is equal to the joint property mass function P of x and y over conditional 1 P of y given x. Or furthermore, we can write it like this: P of x and y can be written further P of y times P of x given y over P of y given x. Now you could see, right, that P of y is a linear function of P of x, and hence H of y is a concave function of P of x as well. Now, condition entropy H of y given x is a linear function of P of x, and hence is a convex function. Then the difference is a concave function of P of x. Now for the second part of the theorem, we consider now that the P of x is a constant. Now we consider two conditional property distribution, let's say P1 of y given x and P2 of y given x, with joint property mass functions as P1 of x and y equal to P of x times P1 of y given x, and P2 of x and y as P of x times P of 2 y given x. Then the marginals of them are P of x and P1 of y and P2 of x, P2 of y. Now consider a new condition probability now as a function of some parameter lambda, as P of lambda y given x is equal to lambda P1 of y given x plus 1 minus lambda P2 of y given x. And this is for every lambda on the interval between 0 and 1, including 0 and 1. Then the corresponding marginal of y is P of some lambda of y equal to lambda p1 of y plus 1 minus lambda p2 of y. And the joint property mass function, let's say q of lambda of x and y, it is p of y times p of y given x, which is as given as lambda q1 of x and y plus 1 minus lambda q2 of x and y. By definition, the mutual information between x and y is equal to the relative entropy of two property mass function, p lambda of x and y and q lambda x and y. Since now relative entropy is a convex function of p and q, it implies that also the mutual information between x and y is a convex function too, which proves the theorem. Next, we are going to introduce the so-called data processing inequality. By definition, first we start with Markov chain. By definition, random variables x and y and z form a Markov chain in the order x, y, z if the conditional distribution of z depends on y and it is conditionally independent on x. That can be written in the following mathematical form. The joint property mass function of z, y, x, y, and z, it is equal to p of x times p of y given x times p of z given y. As a consequences of this definition of the Markov chain, we have the following. The fact that x, y, and z form a Markov chain, then we can start p of x and z given y, it is equal to the joint PMF between x, y, and z over p of y. Or I can write this one as p of x times p of y given x times p of z given y over p of y. This is based on the fact that x, y, and z form a Markov chain. Now, I group together the terms in red, p of x times p of y given x. And this will give me the joint property mass function of x and y. Then I arrive p of x and y times p of z given y over p of y. Moreover, I write in p of x and y in a different form as p of x given y times p of y, then p of z given y as it is over p of y. Moreover, I can simplify p of y over p of y, then I arrive at p of x given y times p of z given y. This indicates that x, y, z forms a Markov chain if and only if x and z are conditionally independent, given y. Now, the second consequence, it is that if x, y, z form a Markov chain, this implies that z, y, and x, or in general, x, y, z, are form a Markov chain in both in the forward direction and backward direction. Moreover, the third consequence is that if z it is a function of some y, then x, y, z forms a Markov chain. Now, we are going to introduce the data processing inequality. If x, y, z form a Markov chain, then the mutual information between x and y, it is greater or equal to the mutual information between x and z. Right? Now you could prove this one using the chain rule for the mutual information from the last week, but now consider only n equal to 2. So this means I have x1, x2. Then the mutual information between of x1, x2, or between x1, x2, and y, it is equal to the mutual information between x1 and y plus the mutual information between x2 and y given x1. Now, if on this expression we take x as y, y as x1, and z as x2, just change on the variable naming, then we arrive at this one. The mutual information between x and y and z, random variables, it is equal to the mutual information between x and y plus the mutual information between x and z given y. Now, again, we take the first expression, but we rename it in a different way, the variables, like x as y, but y as x2 and z as x1. Then we get then the mutual information between x and the pair x, y and z, it is equal to the mutual information between x and z plus the mutual information between x and y given z. Now, since x, y, z forms a Markov chain, then we have said that mutual information between x and z given y, it is equal to 0, because z depends on y, but is independent on x. We have conditionally independent on x. So this makes this mutual information, conditional mutual information equal to 0. All right. Now, as we said, because z, it is independent on x, of x given y. Therefore, the mutual information between x and y, it is equal to the mutual information between x and z plus the mutual information between x and y given z. Now, since the mutual information between x and y given z, it is non-negative, then this implies then the mutual information between x and y, it is greater or equal to the mutual information between x and z, what we wanted to show. Now, we can add to this theorem the second part, which is highlighted in blue in the proof. The equality here holds if and only if the mutual information between x and y given z, it is equal to 0. This means that when x, z, and y forms a Markov chain, or whenever y, it is independent of x given z. This is what would say. Now, we have a corollary, show that if z, it is a function of y, then the mutual information between x and y, it is greater or equal to the mutual information between x and f of y, and between x and f of y. As a proof, since we know that x, y, and z forms a Markov chain, then based on the previous consequences, x, y, and f of y also forms a Markov chain, and using the above theorem that we just showed, the mutual information between x and y, it is greater or equal to the mutual information between x and z. However, z, it is f of y, then we can write that the mutual information between x and y, it is greater or equal to the mutual information between x and f of y, which is what we wanted to show. That implies that for any combinations of the data y, such as f of y, we cannot increase the information about x, right? Whenever x, y, and z forms a Markov chain. So this is something that can be used on the data processing. Now, another corollary, it is the following: show that if x, y, z form a Markov chain, then the mutual information between x and y is greater or equal to the mutual information between x and y given z. Now, again, using the chain rule of the mutual information, with n equal to 1, from the week 2, we have the mutual information between the pair x1, x2, and y. It is equal to the mutual information between x1 and y plus the mutual information between x2 and y given x1. Now we make some changes on the variable. We rename x as y as x1, and z as x2. Then we can write that the mutual information between x and y and z, so between x and the pair y and z, it is equal to the mutual information between x and y plus the mutual information between x and z given y. Now we rename it for a second time as x as a y as x2, and z as x1. Then we get the following. Then the mutual information between x and the pair y and z, it is equal to the mutual information between x and z plus the mutual information between x and y given z. Now, since x, y, z forms a Markov chain, then we can say that the mutual information between x and z given y is equal to 0, because z, it is independent of x given y. Therefore, the mutual information between x and y, it is equal to the mutual information between x and z plus the mutual information between x and y given z. Using the non-negativity of the mutual information, that is mutual information between x and z, it is non-negative, then we can arrive that the mutual information between x and y, it is greater or equal to the mutual information between x and y given z. Here, the equality, which could be as a second part of the theorem, holds if and only if the mutual information between x and z it is equal to 0. That is, if and only if x and z are independent. That implies that the dependence between x and y reduces by the observation of another random variable z. It remains unchanged if and only if the variable z, it is independent of x. Now, as a remark, if x and y and z do not form a Markov chain, then it could happen then the mutual information between x and y to be less than the mutual information between x and y given z. We can illustrate this one with the following example. Consider x and y are two independent fair binary random variables. Fair, it means that they have a probability of occurrence 1/2, such that x and y are drawn from two independent experiments with outputs either 1 for successful or 0 for failure. Now, we introduce z now as x plus y. We want to calculate the mutual information between x and y, and the mutual information between x and y given z. Now, since x and y are drawn from independent experiments, then x and y are independent discrete random variables. Therefore, the mutual information between x and y, it is equal to 0. On the other hand, the mutual information between x and y given z, it is equal to, based on the formula, remember last week, it is equal to the entropy of x given z minus entropy of x given y and z. Or it is equal to entropy of x given z minus entropy of x given z. The reason is because x does not depend on y. So we can remove it from the condition. Then we can arrive to the second line, then replace on the second conditional entropy the z as x plus y. Then we have x, h of x given z minus h of x given x plus y equal. Since again x does not depend on y, we can write it h of x given z minus h of x given x. Then this is equal to h of x given x, it is equal to 0. All right, then we arrive to this one, that all it is equal to the h of x given z. Then this is equal to, we write the conditional entropy as probability of z equal to 1 times entropy of x given z equal to 1. Then this is equal to, the reason is because z takes the value 1. Then this is equal to probability of z being equal to 1, it is 1/2. Then times entropy of x given z is equal to 1, it is 1 bit. Then 1 times 1/2 times 1 gives you 0.5 bits or 1/2 bits, which is greater than 0. All right, so this is the case that we wanted to show. Next, we are going to introduce the so-called Fano's inequality. Let's consider x and y, two discrete random variables, which are correlated. Suppose we know y, and we would like to predict the other random variable, let's say x. Now, suppose that entropy of x given y, which gives the uncertainty on predicting x knowing y. This is also, we gave it last week as a definition. The goal of Fano's inequality is to relate the property of error in predicting x to conditional entropy h of x given y. Note that if y is equal to f of x, then the entropy of x given y, it is equal to 0, right? And the property of error in predicting x by knowing y should be equal to 0. Furthermore, it is expected to predict x knowing y with a small probability of error if entropy of x given y is a small number, but nevertheless, it is non-zero. The Fano's inequality aims to quantify the property of error in predicting x knowing y when the conditional entropy of x given y is small, but still non-zero. Now, the Fano's inequality problem. We would like to predict the variable x with a property mass function p of x drawn from the alphabet chi. We make a measurement on the random variable y that is somehow related to x through the conditional probability p of y given x. Using the observable y, we predict x as x hat equal to f of y, where x hat, it is from the some alphabet set chi hat. Note that f of y is a random variable too. Finding the property of error in predicting x knowing y means that we would like to determine a bound for the property that x, it is different from x hat, which is given as p of error equal to the property of x hat different from x. Note that since x hat, it is equal to f of y, then x, y, and x hat forms a Markov chain. Then the theorem, Fano's inequality theorems, is formulated as the following. For any prediction of x by the estimator x hat, such that x, y, and x hat forms a Markov chain, with property of error equal to the probability that x is different from x hat, we have that entropy with probability distribution p of error plus p of error log with base 2 of cardinality of the set chi, it is greater or equal to h of x given x hat, or it is greater or equal to that h of x given y. Moreover, inequality can be weakened to 1 plus p of e log with base 2 of cardinality of chi greater or equal to the h of x given y, or p of e, it is greater or equal to h of x given y minus 1 over log with base 2 of chi. Here, the 7s can be derived by the equation 6. Now, as a proof, we can first introduce e to be an indicator random variable of error, which is such that e is equal to either 1 or 0. It is equal to 1 if x hat, it is different from x. And it is equal to 0 if x hat, it is exactly x. Now you use the chain rule for the entropy. Then the entropy of e and x given x hat, it is equal to the entropy of x given x hat plus entropy of e given x and x hat. Or I could write this one, just swap the places on the first entropy of x and e, then you get entropy of e given x hat plus entropy of x given e and x hat. Now, furthermore, using the theorem that we showed last week, then the conditional entropy of a random variable x given another random variable, it is less or equal to the entropy of that random variable. Then we have entropy of e given x hat, it is less equal to the entropy of e. But entropy of e, it is equal to the entropy with probability p of e distribution. Since e is a binary valued random variable, all right? Now, since e is a function of both x and x hat, then the entropy of e given x and x hat, it is equal to 0. Moreover, the entropy of x given E and x hat, it is equal to the property of E being equal to 0 times, so I'm using just the definition of the condition entropy, times the entropy of x given x hat and E equal to 0 plus property of E equal to 1 times the entropy of x given x hat and E equal to 1. Now this is less equal to 1 minus P of E times 0 plus P of E log with base 2 of cardinality of chi. Or since the first term drops because I have multiplied by 0, then I have left with P of E log with base 2 of cardinality of alphabet chi. Therefore, the entropy of x given x hat, it is less equal to the entropy of P of E plus P of E log with base 2 of cardinality of chi. Using the data processing inequality, which we showed before, that the mutual information between x and x hat, it is less equal to the mutual information between x and y. And since the x, y, x hat forms a Markov chain, then entropy of x given x hat, it is greater or equal to the entropy of x given y. Therefore, we can write that entropy of x given y, it is less equal to the entropy of x given x hat, or it is less equal to, furthermore, entropy of P of E plus P of E log with base 2 of cardinality of chi. This is what we wanted to prove. Next part, it is the corollary. For any two random variables x and y, if P is equal to the property of x being different from y, then entropy of P plus P log with base 2 of cardinality of chi, it is greater or equal to entropy of x given y. To prove this one, we start using the Fano's inequality. Entropy of x given x hat, it is less equal to the entropy of P of E plus P of E log with base 2 of cardinality of chi. Take y equal to x hat, then P of E is equal to property of x being different from x hat, which is equal to P. And h of P plus P log with base 2 of cardinality of chi, it is greater or equal to entropy of x given y, what we wanted to show. Next, I'm going to talk about the asymptotic equipartition property. Now, first, let me introduce some analogy from the probability and statistics. More precisely, I'm going to introduce the law of large numbers. Consider n independent, identically distributed random variables, IID for short, x1, x2, xn, with some expectation E of x. Then in the limit for large n, or n goes to infinite, for any epsilon greater than 0 but small, we have that the limit when n goes to infinite of this probability, absolute value of 1 over n, sum of I from 1 to n x of I minus E of x, it is greater than epsilon, then this property must be equal to 0. Here, sum of all i's from 1 to n xi 1 over n, it is denoted by x bar and gives the average value. Now, another definition is a sequence of random variables, let's say x1, x2, and so on, converges to a random variable x if in probability, if for every epsilon greater than 0, probability of the absolute value of xn minus x is greater than epsilon converges to 0. In mean square, if the expected value of the xn minus x squared converges to 0. With probability 1, also called almost surely, if the probability of the limit when n goes to infinite, xn equal to x becomes equal to 1. Now, we are going to introduce the so-called asymptotic equipartition theorem. If x1, x2, and so on are independent, identically distributed random variables with probability mass function P of x1, x2, and so on xn, of observing the sequence x1, x2, xn, then minus 1 over n log with base 2 of p of x1, x2, xn converges to h of x in probability. Now, to prove this theorem, since xi for every I, it is a IID, then the functions of xi are IIDs as well. Therefore, log with base 2 of p of xi are IIDs, random variables as well. Using the weak law of large numbers, we have that minus 1 over n log with base 2 of this joint property mass function p of x1, x2, xn, it is equal to minus 1 over n log with base 2. Since the variables x1 to xn are IID, then I can write the joint property mass function as product of the I from 1 to n of the p of xi's. Now I use the property, logarithm property, log with some base of the product, it is equal to the sum of logs. Then I have minus 1 over n, sum of I from 1 to n, log with base 2 of p of xi. Now this one converges, all right, to the minus e of this function, log with base 2 of p of x in probability. Now, moreover, I can write minus inside the log function, then I can write e of this function, log with base 2 of 1 over p of x. But based on the first week, it is the entropy of x random variable, which is a proof of the theorem. Now, we introduce the so-called typical set. The typical set, which is denoted A with some parameter epsilon, n, and the parameter n, with respect to p of x, is the set of sequences x1, x2, xn from some set chi to the power n with this property. The 2 to the power minus n h of x plus epsilon, it is less equal to the joint property mass function, less equal to 2 to the power minus n h of x minus epsilon. Now, next we introduce the so-called typical set theorem. We consider x1, x2, and so on to be some IID random variables with probability, joint probability mass function p of x1, x2, xn for observing the sequence of random variables x1, x2, xn. Then, if x1, x2, xn, it is a n tuple from the a epsilon n, then h of x minus epsilon, it is less equal to minus 1 over n log with base 2 of the joint property mass function, less equal to the h of x plus epsilon. The second part of the theorem, it is that the probability of a of epsilon n, it is greater than 1 minus epsilon for n sufficiently large. And 3, the absolute value of a epsilon n, which is the cardinality of this typical set, it is less equal to 2 to the power n h of x plus epsilon, where here the absolute value a, it is the, as I said, cardinality or the number of elements in the set A. And the cardinality of a epsilon n, it is greater or equal to 1 minus epsilon 2 to the power n h of x minus epsilon for sufficiently large n. We are going to prove all these 4 parts of the theorem in the following. We first prove the first part using the definition of the typical set, 2 to the power minus n h of x plus epsilon, then this is less equal to p of x1, x2, xn, less equal to the 2 to the power minus n h of x minus epsilon. Now take the log with base 2 of both sides and divide by minus 1 over n. Note that when you divide by minus 1 over n, then the sign of inequality changes direction. Then we get this one, h of x minus epsilon, less equal to minus 1 over n log with base 2 of p of x1, x2, xn, less equal to h of x plus epsilon. And this is what we wanted to show. Now, on the second part, we use what we derived from the first part of the theorem, minus 1 over n log with base 2 of p of x1, x2, xn converges to h of x. Therefore, for every delta which is positive, greater than 0, exists n0 such that for every n greater or equal to n0, we can write probability on the absolute value of minus 1 over n log with base 2 of p of x1, x2, xn minus h of x less than epsilon, it is greater than some 1 minus delta. Taking delta as epsilon, then we get probability of absolute value of minus 1 over n log with base 2 of p of x1, x2, xn minus h of x being less than epsilon is greater than 1 minus epsilon, which is a proof of what we wanted to show. All right, now we start. There is a short break, We start this third part of the theorem. So we start using the normalization property of the probability. Let's take the vector x as this n tuple x1, x2, xn, which is from chi to the power n. Then I have 1, it is equal to the sum of all x's vectors from chi to the power n, p of x vector. Now, if I say the typical set, it is a subset of chi to the power n, then this sum, since p of x are numbers between 0 and 1, then this sum it is greater or equal to the, if I sum all x's vectors from the a epsilon to the power n p of xa. Now, this is moreover based on the previous theorems, that this is greater or equal to the sum of all x from a epsilon n 2 to the power minus n h of x plus epsilon. Now, this is furthermore equal to, since the 2 to the power minus n h of x plus epsilon does not depend on the vector x, I can bring it outside. Then I have 2 to the power minus n h of x plus epsilon. Then sum of all x's from A epsilon will give me the cardinality of the A epsilon n set. Therefore, we can rearrange this one. Then you get that the cardinality of A epsilon n, it is less equal to 2 to the power n h of x plus epsilon, which is a proof. Now the fourth part, for large n, we have 1 minus epsilon. It is less equal to the probability of A epsilon n, which is less equal to the sum of all x's from x vectors from A epsilon n 2 to the power minus n h of x minus epsilon, which is equal to 2 to the power minus n h of x minus epsilon times the cardinality of A epsilon to the power n. And hence we get that cardinality of A epsilon n, it is greater or equal to 1 minus epsilon 2 to the power n h of x minus epsilon, which is also a proof of this. Next, I'm going to give you some extra exercises. Prove or disprove the following. Let x and y, z be random variables in the following. All right? H of x given z minus h of x given y and z, is it equal to h of y given z minus h of y given x and z? H of z given x minus h of z given x and y, is it equal to h of y given x minus h of y given x and z? Moreover, mutual information between x and z given y, is it greater than or equal that the mutual information between z and y given x minus mutual information between z and y plus mutual information between x and z? Let z be x plus y. Would I have the following? H of z equal to h of x plus h of y? Now, we start proving each of these. Using the chain rule of entropy, we have the joint entropy of x1, x2, xn. It is equal to the sum of the conditional entropies, I from 1 to n, h of xi conditional on xi minus 1 up to x1. Now, take this one for n equal to 3. Then you can have that the joint entropy of x1, x2, x3, it is equal to the h of x1 plus h of x2 given x1 plus h of x3 given x2 and x1. Taking y equal to x2, z equal to x1, and x equal to x3, then you get h of x, y, and z, it is equal to h of z plus h of y given z plus h of x given y and z. Taking x equal to x2, z equal to x1, and y equal to x3, then you have h of x, y, and z, it is h of x plus h of x given z plus h of y given x and z. From the last two equations, you get h of z plus h of y given z plus h of x given y and z, it is equal to h of z plus h of z x given z plus h of y given x and z. Or you could rearrange it, h of x given z minus h of x given y and z, it is equal to h of y given z minus h of y given x and z. Now, again, for a second part, take z equal to x2, x equal to x1, and y equal to x3. Then you get h of x, y, and z, it is equal to h of x plus h of z given x plus h of y given z and x. Then take y equal to x2, x equal to x1, and z equal to x3. Then you get h of x, y, and z, it is equal to h of x plus h of y given x plus h of z given y and x. Using the last two expressions, you have h of x plus h of z given x plus h of y given z and x plus equal to h of x plus h of y given x plus h of z given y and x. Or you could say have h of z given x minus h of z given y and x equal to h of y given x minus h of y given z and x. What we wanted to show as a second part. Now for the third part, you could use the chain rule of the mutual information. I, mutual information between x and z given y, plus mutual information between z and y, it is equal to mutual information between x, y, and z, equal to mutual information between z and y given x, plus mutual information between x and z. Or you could rearrange, then you get h of x, mutual information between x and z given y, equal to mutual information between z and y given x, plus mutual information between x and z minus mutual information between z and y. So indeed, it's not inequality, but it is equality in all cases. A second exercise, consider a measure of correlation. Let x1, x2 be identically distributed, but not necessarily independent. Let's define rho as 1 minus h of x2 given x1 over h of x1. We have to show that rho it is equal to mutual information between x1 and x2 over h of x1. Rho it is between 0 and 1. And we have to find out when rho it is equal to 0 and when rho it is equal to 1. Now, since x and 1 are identically distributed random variables, such that rho it is equal to 1 minus h of x2 given x1 over h of x1, then we can rearrange this one, write it as h of x1 minus h of x2 given x1 over h of x1. All right, then you could, since h of x1 it is equal to h of x2 because they are identically distributed random variables, then we have h of x2 minus h of x2 given x1 over h of x1. But the h of x2 minus h of x2 given x1 is the mutual information between x1 and x2, then we arrive what we wanted to show. Now, next, using the fact that the conditional entropy of x2 given x1, it is non-negative, however, it is less than h of x2, or it is equal to, which is equal to h of x1. Therefore, we have that h of x2 given x1 over h of x1, it is between 0 and 1, which means that rho it is between 0 and 1. From the expression for rho, you could see that rho it is equal to 0 if and only if the mutual information between x1 and x2 it is equal to 0, where the last is true if and only if x1 and x2 are independent. On the other hand, rho it is equal to 1 if and only if h of x2 given x1 it is equal to 0, or by symmetry, if and only if h of x1 given x2 it is equal to 0, which is true if and only if chi2 it is is a subset of chi1, or by symmetry, if and only if chi1 it is a subset of chi2. So this means that, or hence from here, chi1 it is equal to the chi2. Consider another example of coin flips. A fair coin is flipped until the first head occurs. Let x denote the number of flips required. Find the entropy of h of x in bits. The following expression might be useful. That sum of n equal to, from 0 to infinite, r to the power n, it is equal to 1 over 1 minus r, and sum of n r to the power n, n from 0 to infinite, it is equal to r over 1 minus r squared. A random variable x is drawn according to this distribution. Find an efficient sequence of yes/no questions of the form is x contained in the set S. Compare h of x to the expected number of questions required to determine x. Now, from probability and statistics course, you might have taken this one. Let x be the number of flips until the first head appears. Then x is a random variable following the geometrical distribution. So this means probability of x being equal to n, it is equal to p times 1 minus p to the power n minus 1, where p is equal to 1 over 2 and n it is from the set 1, 2, and so on. Now, the entropy of x can be calculated as the following, equal to minus sum of n from 1 to infinite, p of x equal to n, log of with base 2 of p of x equal to n. Then you replace probability as p times 1 minus p to the power n minus 1, then you have log with base 2 p of times 1 minus p to the power n minus 1, and sum from 1 to infinite. Now we can write the log with base 2 of product as sum of 2 logs, then we can write the whole sum as 2 sums. Sum of n from 1 to infinite, p of 1 minus p n to the power minus 1 log with base 2 of p, plus the second sum n from 1 to infinite, p of 1 minus p n to the power minus 1 log with base 2 of 1 minus p to the power n minus 1. Then we can further introduce m as equal to n minus 1, then sum becomes m from 0 to infinite, p times 1 minus p to the power m log with base 2 of p. And the second sum becomes m from 0 to infinite, p 1 minus p to the power m log with base 2 of 1 minus p to the power m. You could further write, since p log with base 2 of p on the first sum does not depend on m, I can bring it outside, and I have minus p log with base 2 of p, sum of m from 0 to infinite, 1 minus p to the power m, plus on the second sum, I can write this one as p 1 minus p log with base 2 of 1 minus p, the derivative with respect to p of this sum m from 0 to infinite 1 minus p to the power m. Then I can use the fact that the sum of m from 0 to infinite 1 minus p to the power m, it is equal to 1 over p. Then I get minus p log with base 2 of p over p minus p 1 minus p log with base 2 of 1 minus p over p squared. Then you can group this together. Then you get h of p over p. And since h of p is equal to 1 bit for p equal to 1 over 2, then you get 1 bit over 1 over 2, which is 2 bits. Now, for the second part of the theorem of the exercise, intuitively, it seems clear that the best questions are those that we have equally likely chances of receiving a yes or no answer. Consequently, one possible guess is that the most efficient series of questions is x equal to 1? If not, is x equal to 2? And we can continue this way. If not, is x equal to 3? And so on. The expected number of questions equals to this number, sum of n from 1 to infinite, n times 1 over 2 to the power n, which is equal to, if r it is taken as 1 over 2, then this will represent r times the derivative with respect to r of this sum n from 1 to infinite r to the power n. Then I can further write this one, r d to the over dr. Then I can write this one r times, then I change the summation index from n to m from 0 to infinite r to the power m. Now the sum, it is equal to 1 over 1 minus r. Then I have r d over dr, r times 1 over 1 minus r. M, it is equal to n minus 1. Then I can calculate the derivative. Then I have r 1 times 1 over r, 1 minus r plus r times 1 over 1 minus r squared. Then this gives you r over 1 minus r plus r squared over 1 minus r all squared. Then for r equal to 1 over 2, then this becomes equal to 2, which equals the entropy of x. As a summary, you should know about the data processing inequality theorem. You should know about the Fano inequality theorem. You should know about the asymptotic equipartition property. You should understand working with exercises with conditional Shannon entropy. As a reference, please look at this literature, An Introduction to Information Theory from the Lambert Academic Publishing, and the Elements of Information Theory from Carver and Thomas, published on Wiley & Sons in 2006. Thank you for your attention. I'll see you next week.